Hi, I'm Laura, and this is my channel where I talk about work, life, and everything in between. Last time I gave a deep dive into the data preparation portion of the modeling process. In this video, I will talk about general modeling concepts that a credit risk modeler should know. Then I will dive into actual modeling process and techniques. Once you get into this area, you can get pretty deep into the methodology, but I'm just scratching the surface. This video will get pretty technical, so feel free to leave questions if you want to understand anything better. First, as a recap, credit risk is the risk that a borrower won't repay their debt, which may result in a loss for the bank. In modeling, we often break this down into three components. Probability of default, which is the chance the borrower will default within a time horizon. Loss given default, which is how much we expect to lose if they default. And exposure at default, which is how much is at stake when they default. Depending on the use case, we might model one or more of these components. For example, PD models or models that predict delinquency could be used for approval decisions, while all three models could be relevant for capital calculations. We often classify the models by their business purpose or use case. Application models and strategies predict risk at the time of application using static data like credit score and income, and make decisions based on a score cutoff. Behavioral models track how customers behave over time and look at payment patterns. Collections models forecast repayment likelihood for delinquent customers. Regulatory models, which are designed to estimate specific risk measures for regulatory purposes like capital adequacy and allowance. When designing credit risk models, another key concept to consider is whether our model is meant to reflect point-in-time risk or through-the-cycle risk. Point-in-time models estimate risk based on current economic and borrower conditions. They react quickly to changes, making them suitable for short-term decision-making, like whether to approve a loan today. During a downturn, a point-in-time model might show rising default risk. On the other hand, through-the-cycle models smooth out short-term volatility and aim to estimate long-term average risk over the full credit cycle. These are more common in regulatory capital models. A through-the-cycle model would produce a more stable estimate, assuming that downturns and upturns balance out over time. It's important to distinguish the purposes between point-in-time and through-the-cycle models because business models like application scorecards often use point-in-time to stay responsive to changing risk, while regulatory models, particularly for capital estimation, often use through-the-cycle to avoid pro-cyclicality. Understanding this distinction helps explain why different models might give different risk estimates, and why they're both valid in their respective contexts. If your model user is expecting your model to be reactive to changes in economic conditions, but you've built a TTC model, then you're going to get a lot of calls. In my business understanding and regulations video, I mentioned that expected losses are losses that are part of doing business, and unexpected losses are extreme levels of losses that may happen which are hard to predict. The type of loss you are modeling will impact your model design as well, since expected losses are about forecasting and provisioning and trying to make sure your model is accurate, whereas unexpected losses are about resilience and capital adequacy and trying to make sure your model is conservative enough. Now let's talk about the modeling process. So we're assuming that we're starting from where we left off in my previous video about data preparation and that we already have most of our data prepared. This means that we have the data in the format that we'd like, we have our target variable defined, and we have the features we'd like to test for including into our model. When considering what modeling approach to use, we need to first be clear on what exactly we would like the model to do, what is the target we are trying to predict, and define what would make the model successful. Do we want the model to give a precise loss estimate, or is it more important that the model is conservative, even if it could overestimate the loss? You would need to get a good understanding of the context that the model would be used for. If this model will be used for a specific business purpose, you will want to connect with your business partners to understand what their goal is and how that translates into model design. If you are building a model for regulatory purposes, you would want to refer to the relevant regulatory document for requirements. Then we consider the data we have available in order to achieve those success criteria. For example, if you have more granular data at loan level or transaction level, then your approach will be different than if you only had portfolio level summary data, which wouldn't allow for more complex approaches. Ultimately, your selection for modeling approach should be logical and fit for purpose. Some common credit risk modeling approaches include classic approaches, such as logistic regression. This is most widely used for PD modeling, and it predicts the probability of default with a binary outcome, default or not. It is commonly used because it's transparent and interpretable, easy to implement and monitor, and is generally accepted by regulators. Linear regression. This is used for LGD and sometimes EAD modeling with continuous outcomes. It is also simple, transparent, and interpretable. Scorecards. This is typically used to provide a credit risk rating or score used in application or behavior monitoring, and it is common in retail credit risk. Each feature is given a weight and is binned with a corresponding score for each bin. Some more specialized statistical approaches include survival analysis and hazard models, which models time to default rather than just the probability, so it gives more flexibility if we want to look at different default windows. Markov chain models, which model transition probabilities between different credit states, like from current to delinquent to default. Bayesian methods, which can incorporate expert judgment and prior assumptions, which can be helpful when the data is sparse. There are also machine learning approaches, including decision trees, which are easy to interpret and can handle non-linearities and interactions. Random forests, boosting, and neural networks, which utilizes ensembles of simple models to achieve higher predictive power and to capture nonlinear relationships. However, they are less interpretable. These are often used in challenger models to see how well the model performance can get. In practice, we rarely have perfect data or a perfect understanding of future risk, especially during economic downturns. That's why sometimes we can incorporate conservatism into our models to avoid underestimating credit risk. Conservatism can be added in different ways. Data adjustments. For example, if recent data may not reflect adverse conditions, we may override or weight data to emphasize the downturn period. Parameter floors and caps. Setting minimum or maximum values for parameters like PD or LGD to ensure they don't fall below historically reasonable thresholds. Margins of conservatism. This is a formal concept under regulatory frameworks like Basel, where we add buffers to account for model uncertainty or data limitations. Stress testing. Models can also be tested under stress scenarios, and the results may inform conservative adjustments or overlays. The modeling approach will give you the general structure of the model. Then you'll need to decide which features go into the model. Once you collect the data and understand the business context, the next crucial step is exploratory data analysis, EDA, and feature selection. Exploratory analysis is where we dig into the data to identify patterns, outliers, and relationships between variables. We look at distributions and correlations, and we start to get a sense of what might drive credit risk outcomes like default or loss. The steps to the exploratory analysis include summary statistics for each variable, like mean, median, and percentiles, and visualizations like box plots and histograms to understand how the data is distributed. Is it bunched close to the mean, or is it dispersed? Is the distribution skewed? This kind of analysis helps us to identify if a variable needs transformation, if it's heavily skewed, or if it should even be included. Bivariate analysis looks at the relationship between two variables, especially against the target variable, for example, the default flag, in order to see which variables are associated with the target. When each feature is plotted against the target, you'll be able to see potential trends which will help you identify which variables are likely to be predictive. For example, if we find that default rates increase significantly at lower income levels, that tells us income is likely to be an important feature. Sometimes we also explore interactions between two features, especially if we suspect multicollinearity, meaning the two features are highly correlated, so they are redundant, or if there's a non-linear relationship that might need transformations or binning. By doing these analyses, you will get an understanding of the data quality, potential predictive power, and even uncover business insights, all of which are key inputs to model development. Once we understand the data, we move on to feature selection, the process of choosing the variables that are most predictive, stable, and interpretable while avoiding redundancy. There are statistical techniques for feature selection, but even before statistical tests, we consider if the feature makes intuitive sense in the context of credit risk. For example, a borrower's income level or their delinquency history is obviously related to their ability or willingness to repay. Domain knowledge ensures that we don't include spurious correlations that don't actually reflect credit behavior. Furthermore, your exploratory data analysis would also inform you which features may be predictive. With that out of the way, now let's get into some statistical techniques for feature selection. A common technique is to compute predictive power metrics for each feature and to keep only the top features with the highest values in these metrics. For classification models which have distinct outcomes, like default or no default, we can calculate information value and weight of evidence. For continuous models, like loss rates, we can use R-squared, AUC, or other feature importance scores. However, simply doing this may ignore interactions between features that can predict a target, or result in redundant features being selected if they carry the same information. This is where correlation analysis between features come in, and if two features are highly correlated, we would pick only one of them. Another technique is to use machine learning models and look at feature importance rankings, which are part of some of the model's output. For tree-based models like random forest or gradient boosting, you can extract built-in feature importance scores. However, this method is also prone to issues when there is multicollinearity. Stepwise selection is refitting the model each time, adding or removing a feature until we get to the model with the best performance. Common ways to do this include forward selection and backward elimination. Forward selection is starting with an empty set and iteratively adding the feature that provides the best improvement in model performance. Backward elimination is starting with all the features and iteratively removing the feature that least impacts the model performance. By doing stepwise selection, redundant features are unlikely to be chosen as they will not provide improvements to the model performance. Regularization is a process built within the model training process that can also achieve feature selection. It penalizes the model for having too many features, so the training algorithm would need to choose the features that really add predictive value. Even with these techniques for feature selection, it's really important at the end of the day to select features that make business sense and are not too convoluted, so that you can explain your model to your stakeholders. This helps build trust with your model users. Once you've selected your features, it's time to fit your model. This is where we decide which algorithm or statistical technique is most appropriate for the business problem we're trying to solve, and then rigorously test it to ensure that it performs well not only in our sample, but also outside of our sample. When you fit a model, you are specifying what approach you will be using, what dataset you are using, what is the target, what features will be in the model, any configurations that are relevant to the approach you use, such as which loss function to use, model hyperparameters, which are used in machine learning models to define their structure and learning process. The model fitting algorithm will take these specifications and calculate the model parameters based on the data. It will give you the resulting model specification, which is the exact mathematical formula that connects your features with the target. For more complex models like machine learning models, it will be difficult to view the exact mathematical formula, but rest assured the formula is being saved in your model. To compare models, we evaluate their performance across several dimensions. 1. Discriminatory power. Can the model separate good and bad borrowers? Common metrics here include Gini coefficient and area under the ROC curve, also known as AUC. 2. Calibration. Are the predicted probabilities or values close to the actual outcomes? A model with good calibration doesn't just rank risks well, it also gets the levels right. Calibration metrics include the Brier score for probabilities, or more generally, mean squared error. 3. Stability and robustness. Does the model behave consistently across different subpopulations or over time? This is key for risk models that will be used for years. A way to measure stability is the Population Stability Index, which measures the difference in the distribution of data features between the training data and the new data. A high PSI indicates significant drift and potential instability. 4. Interpretability. Can we explain how the model works? For regulatory models, especially under Basel or IFRS 9, interpretability is crucial. Then we select the model that gives you the best results across these dimensions, based on whichever dimension is most important for your use case. After we select the model, we move on to model testing. This involves checking how well the model performs on data it hasn't seen before. This is typically done by splitting our data into training and testing sets. Sometimes we also include a validation set to fine-tune hyperparameters without biasing the test results. The test metrics could be the same as the evaluation metrics we covered in the model comparison dimensions, so this could seem repetitive. However, the key to model testing is to check that the selected model can perform on new data that was not used for training and model selection. In some cases, we'll use cross-validation, where the data is split into multiple subsets and the model is trained and tested several times to ensure stable performance. Besides performance metrics, we also run tests such as backtesting, which is looking at the model's predictions versus the actual values through time. Benchmarking, which is comparing our model's performance against a benchmark model that could be an industry standard or another internally developed model. Sensitivity analysis, which is seeing how much the model outputs change relative to tweaks to the model inputs, and seeing if that change makes sense. Stress testing, which is inputting extreme values of the inputs to see if the outputs still make sense, and in credit risk, it's common to use severe economic downturns or interest rate shocks. Ultimately, model selection and testing isn't just about choosing the most predictive model. It's about choosing the model that best balances predictive power, interpretability, and compliance. Because in credit risk modeling, being right isn't enough. You also need to be understood, validated, and defensible. It's a general misconception that a model developer just needs to develop a model that performs well on tests and then we're done. One often overlooked but absolutely crucial part of credit risk modeling is model documentation. As a model developer, especially in risk, it is as important to develop a good model as it is to document and explain your choices on how you arrived at that model. It's not just about writing things down. It's about creating a transparent and reproducible record of what the model does, why it was built that way, and how it should be used. We need model documentation because of 3 main reasons. 1. Transparency. Stakeholders, including model validators, auditors, regulators, and internal users, need to understand the model's design, assumptions, limitations, and performance. 2. Credit risk models need to be independently validated as part of regulatory requirements, and your model documentation is a key deliverable for validation. Without clear documentation, a model can't be properly challenged or approved. 3. Continuity. If the original model developers leave, their knowledge shouldn't leave with them. Documentation allows others to maintain or rebuild the model if needed. When you write model documentation, you need to write about the what, the how, and the why. This means as you write, you need to think about these questions. What model did you build and how did you build it? Which data sources you used? What tools you used? What approach you used? What metrics you used to define model success? Why did you take the steps that you took and build the model the way you did? Did you consider alternative approaches? Why choose the one you selected? What makes you comfortable that the data you used is complete and accurate? Why did you select those features in the model? If you made some assumptions in the model, what evidence do you have that those assumptions are reasonable? Typical sections within model documents include business context, data sources, methodology, model assumptions and limitations, performance metrics and testing, governance history and version control, as well as references and appendices. In addition to written descriptions, the model documentation is filled with tables and plots and analysis that support your modeling choices. There needs to be clear rationale for what you did. Sometimes justifying what you do can be a significant amount of work, so don't overlook this part. And that wraps up this deep dive on credit risk modeling techniques. If you found this video helpful, please give a thumbs up and subscribe. Have questions or thoughts? Drop them in the comments. I'd love to hear from you. Thanks for watching. Bye.